Hello, Math 31 Calculus students. You are today learning about higher order derivatives. So once you know how to do one derivative, why wouldn't you want to do it twice? Um, in a nutshell, derivatives are slopes, as we said. So a derivative can be interpreted as the slope of the tangent line. So if you're dealing with a position versus time graph, then on that graph, when you take the slope of position in meters versus time, so whatever the graph is doing, when you take the slope of that graph, that would be measured in change in y over change in x. So change in meters versus change in time in seconds. So in that case, the slope, which is equal to y prime, would be equal to meters per second, or in that case, velocity. But if you were taking, change of displacement or velocity, but when you take the slope of a velocity graph, which would be the second derivative, so in this case, the slope of that graph would be y double prime, then you would be still looking when slope, you'd be looking at change in velocity over change in time. So now you're going to have meters per second per second. So when you take the second derivative, you're really looking at acceleration. Excuse me. So that's the purpose of taking a second derivative and others. The next thing is that in terms of notation, we can talk about Newton's notation and primes. So y double prime, f double prime. There's also several different books use different versions of Leibniz. So d2f at x, d2x f at x, d2xy at x, and then there's also this one, which is one we normally see when we're dealing with Leibniz notation, right? So let's do three examples, and then we'll send you off on your journey to do the questions. And this is a start, and then you're going to see some ones that are a little more interesting in your work, right? So example one, first derivative, just looking at what it is. So y equals x to the 6, so therefore y prime would equal 6x to the 5, and therefore y double prime would equal 30x to the 4, and all was good. So if they were all like that, they'd be pretty easy. Now, obviously, we're going to find questions where we have to use these rules in deep and scary ways. And so number two, obviously, we can see we're going to need to use the chain rule. So for that one, y prime in its first derivative is going to be 8 times 4 minus x squared to the 7 times, in this case, minus 2x, the derivative of the inside. My suggestion would be before you just kind of roll along and start taking the next derivative, you should try and simplify if you can. So I can put these two coefficients together. I'm going to turn that into minus 16x, 4 minus x squared to the 7. And so now on the second derivative, okay, therefore I take my second derivative and y double prime is equal to, and we can see that now we're going to have to use the product rule, so f times g, along with the chain rule as well. So when I take that derivative, you end up with y double prime equal to, y double prime equal to minus 16 times 4 minus x squared to the 7 plus minus 16, 7, 4 minus x squared to the 6 times a minus 2x using product rule and chain rule. You need to do some simplifying, so that can be minus 16. We'll just leave this alone. 4 minus x squared to the 7. We can put all this together as positive 224x and a 4 minus x squared to the 6. You can see there's a common factor, so I can take out a minus 16 and a 4 minus x squared to the 6. And I would be left with 4 minus x squared to the 1 and plus 14x, which in your final step simplifies to be y double prime equals minus 16, 4 minus x squared to the 6, and minus x squared plus 14x plus 4. And all was good in number 2. Okay. And for the last example, we need to be able to do second orders with implicit differentiation too. So when you have 3x squared, excuse me, when you have x cubed plus y cubed is equal to 5, and you take your first derivative, right? I'm going to end up with 3x squared plus 3y squared, y prime, equals 0. I solve it for y prime, and I end up with minus 3x squared divided by 3y squared. Excuse me, which ends up being minus x squared over y squared. But that's just the first derivative. So in the second derivative, we take the derivative again. Therefore, that would make it y double prime. We obviously have to use, excuse me for the coughing, we obviously have to use the quotient rule. So with the quotient rule, I get y squared, and I get a minus 2x f prime times g, which is x squared, minus f, which is minus 2x times, sorry you guys, times the derivative of g, which would be 2y y prime. And you might think you're done, but you cannot leave this. You have to substitute your original y prime back in there and then simplify it so you don't have a single prime inside this one prime. So I have minus 2xy squared, that's fine. This part here is going to be a positive 4 pausing. Sorry guys, I just needed to go back and fix this. So we did this part correctly. That was f prime g, but we didn't do this correctly, or I didn't do this correctly. So that was supposed to be f, which would be subtract minus x squared, right? So minus x squared times 2y y prime. So that would be positive 2x squared y prime all over y squared. This y prime can now become, right, so we substitute in there, and that has to become x squared over y squared minus, right, minus x squared over y squared. And when we do that, we have to simplify. So y double prime equals minus 2xy squared minus 2x to the fourth over y all over y squared. Now we can't leave a complex fraction like that, so we multiply the whole top by y and the whole bottom by y, and we end up with y double prime is equal to minus 2xy cubed minus 2x to the fourth all over y to the 5. Now the reason it's y to the 5 is because I'm a goofball, and if you look back to our quotient rule all the way along, and you guys probably caught this, but in my zest to get your notes done, I need to make sure that I'm doing it properly, and that's why that final answer needs to be that. So twice the fun for the same low price. Higher derivatives. Complete your assignments and we will talk to you in class.